Welcome back to my lecture about James space from functional analysis, or more precisely, Banach space theory. At the end of the last lecture, we proved a result that there is a norm with which we can renorm a Banach space to make its basis monotone. And we will now derive quickly some corollaries and then show how this new norm is tightly connected with the original basis and its monotony. All right, so we will begin with corollary 1.8, which is that the natural projections are continuous. So how will we prove this? Well, according to the proof of theorem 1.7, there is a constant c greater than 0, such that the norm of the projection of a vector which has this form, well, this is just the same as the nth partial sum, and this is per definition less than or equal to the norm of the entire vector, but now we use the xn norm, right? Because this was the supremum over all the partial sums, and this is now less than or equal to c times the norm of the entire vector. And thus, the natural projections are bounded and continuous. And corollary 1.9 is that the coordinate functionals are also continuous. Here's the proof. For m bigger than 2 or equal to 2, we have that the norm of the mth coordinate functional is just the same as the supremum over all elements y with norm 1 of the values of this coordinate functional at those points. This is just the definition of the functional norm. Now we multiply on that a1. We do this in the following way. We get ourselves the norm inverse of the mth basis vector. Here we have our supremum. And now we just add the vector here, right here. All right. Well, and this is the same as this norm inverse times the supremum. And now we rewrite this expression in the following way, using our natural projections. And this is less than the supremum of the norm of Pm times the norm of y plus the norm of Pm minus 1 times the norm of y. And this is obviously less than or equal to xm norm minus 1 times 2k. And why is this? Well, the norms of the elements y are just 1, so we can ignore those, and the norms of the natural projections are smaller than the basis constant per definition of the basis constant. And for m equals 1, we will find a similar inequality. I will spare you the details, but this will just be smaller than this. A quick note: we can extend every definition that we make for bases, for Schauder bases, to the realm of basic sequences, because a basic sequence is a basis on its closed linear hull. As such, it can have a basis constant, it can be monotone. So whenever I speak about a basic sequence being monotonic or having a basic constant such and such, I mean it in the way that this is the basic constant of the basis that this basic constant is on its closed linear hull. I hope you could follow that, and we will continue now with a nice lemma. The basis constant, k, is the smallest real number m greater than 0, such that the norm of the mth partial sum of a vector is less than or equal to m times the norm of the whole vector. It's also the smallest real number m greater than 0, such that the norm of the mth partial sum is smaller than or equal to m times the norm of the m plus 1th partial sum. So this makes the basis constant a pretty useful number. Here comes the proof. Recall that for a linear bounded operator, T going from a normed space X to a normed space Y, we have the following way to characterize its operator norm. Norm of T is the same as the infimum of all numbers L greater than 0, such that for all vectors, we have that the norm of Tx is less than or equal to the norm of x times L. Okay. Now, for all m in n, we have that the norm of the mth partial sum is less than or equal to the norm of the mth natural projection times the norm of the whole vector. And from this, the first claim follows. So let's give these numbers. We call this 1, we call this 2. So 1 follows. And 2 follows from the following observation, that the norm of Pm1 of a vector is the same as the norm of Pm1, Pm2 of the vector, and this is smaller than or equal to the norm of the natural projection Pm1 times the norm of Pm2 of our vector. For all m2 greater than m1. obviously. And this concludes our proof. Now we will show a proposition. So let X be a Banach space and Xn a basis of that Banach space. Then the following statements are actually equivalent. First, Xn is monotonic, so it has basis constant 1. The second statement is that for all m and for all vectors from X, we have that the norm of the mth partial sum of this representation is less than or equal to this. You can imagine this follows trivially from the lemma that we just proved. The third statement is that for all m element n and for all scalars alpha 1 up to alpha m plus 1, we have the following inequality. And finally, the fourth statement is that actually the norm and the other norm xn that we defined in last video are not only equivalent, but the very same. So actually the only way that a basis can be monotonic is if the space we are talking about is already equipped with the xn norm in the first place. So proof, and as I have already indicated, most of this follows trivially from lemma 1.10, and lemma 1.10 tells us that indeed 1 and 2 and 3 are all equivalent. Now what's interesting and left for us to prove is the equivalence of the third and fourth statement. So that is what we are going to prove now, that this is equivalent to this. Okay, now first we know that if this holds, for all m, this implies that the limit as m goes to infinity of the norm of these mth partial sums is the same as the supremum. Of course, we take the supremum over n. And then it follows that the norm of the vector, well, this is just the same as the limit as m goes to infinity of the norm of the mth partial sum. And, well, as we have just seen, this is the same as the supremum over m in the natural numbers. And what is this? Well, this is simply the definition of the xn norm of the vector. And Thus, we are done with this proof. Okay. And now we shall move on to a bigger theorem. Here I've called it a lemma, and so I have to call it a lemma now too, but it's actually a pretty nice theorem. It's called the Grinblum Criterion, named after the Soviet mathematician Grinblum. So, what does this mathematician tell us in his lemma? Let's give it a name. It's the Grinblum Criterion. All right. And what does this tell us? Well, it tells us that a sequence xn is a basis if and only if the following three statements hold true. First, all of the vectors xn must be non-zero. Secondly, there must be a real number m greater than 0 such that the m1th partial sum is less than m times the m2th partial sum for all m1 and m2 natural numbers with m1 smaller or equal to m2 and scalars alpha 1 up to alpha m2 from our field K. Okay, and the third statement that must hold true is that the closed linear hull of the xn's must already be the whole space. Okay, so let's prove this now. First up, I will mention that a basis does fulfill all three criteria. All xn are non-zero because otherwise the representations would not be unique. And secondly, the basis constant is the number m that we search in this second statement. And the third statement is rather obvious from the definition of a basis. So we conclude that every basis does fulfill the Grinblum criterion. However, now we want to prove the interesting part, that every sequence which does fulfill this Grinblum criterion is actually a basis, a Schauder basis. So let's take a sequence xn which does fulfill all these three properties, and then let beta n and gamma n be sequences of scalars such that these two sums here both converge and are equal. So this is an equal sign, all right. Then we observe that the difference of beta 1 and gamma 1 times the norm of the first basis vector, or the first vector of our sequence. We don't know yet if it is a basis, but that will be proven soon. This is the same, obviously, as beta 1 minus gamma 1 times x1 in the norm. This is just the absolute homogeneity, nothing special here. And now we get this inequality from our second property. And since these are equal, this is equal to 0. So as this product at the very front right here is 0, and the vector x1 has norm not 0, we conclude that beta 1 minus gamma 1 is equal to 0. We repeat the argument in the following way for beta 2 and gamma 2. But now, since we already know that beta 1 is equal to gamma 1, and when we pull this in, we can then write this as such. So this sum goes from 1 to 2. And, well, this is then less or equal to m times. And again, this is 0, because this is 0, right? And so we conclude again that beta 2 is equal to gamma 2. And now we repeat this argument over and over again, and by induction, we get that beta n is actually the same as gamma n. So what we have proven right now is that if there is a representation with respect to this, well, maybe basis, then this representation is unique. So that is nice. Now, for all m from the natural numbers and every sequence of scalars which has only finitely many, indices j such that alpha j is not 0, we let Pm, small p, of a vector alpha n xn be defined as the mth partial sum of this. So we can talk about this because only finitely many alphas are not 0. So there are only finitely many dimensions that actually exist in this vector. We can talk about this as a mapping from the linear hull of the xn's into the linear hull of x1 to xm. Okay, think about that for a second. And this is a bounded operator, so Pm is bounded with norm less than or equal to m. And as this is dense, we find a linear bounded continuation of Pm on the whole space X, and we call this capital Pm. This now goes from X to the linear hull of x1 to xm. And this Pm also has a norm less than or equal to m. Now, for all x in X and y in this span, and for all m a natural number, we have the following: the norm of Pmx minus x. Now we use the triangle inequality, which is less than Pmx minus Pmy plus Pmy minus y plus y minus x. Well, this is less than or equal to m plus 1 times the norm of x minus y. And what remains is the norm of pmy minus y. And so we get that the lim sub, as m goes to infinity, of pmx minus x is less than or equal to m plus 1 times x minus y. And this holds for y being an element of the linear hull of all the xn's. Okay. Now, since y is an arbitrary member of a dense subset of x, it follows that the lim sub, as m goes to infinity, of pmx minus x is just 0. And this just means that the limit as m goes to infinity of pmx is simply x. So these pm's seem to be pretty much our natural projections. Now for the final step, we fix x element of x and we find an alpha 1 from the field K such that p1x equals alpha 1 times x1. Now this follows because p1 sends x into this linear hull, which is only spanned by x1. Now for every y such as this, we have that p1 of p2 of y is just p1 of y. And since this is on a dense subset, we know that p1 is actually the same as p1 and p2 combined like this. Therefore, there exists alpha 2 in our field K such that p2 of x is the same as alpha 2 of x2 plus alpha 1 of x1, since p2 of x is an element of the linear hull of x1 and x2. And you can imagine what we will do now. Again, we will make an argument per induction and find that there is a sequence alpha n such that Pm of x is the same as the mth partial sum of alpha n xn. And thus we have that x is the same as the limit of pmx as m goes to infinity, which is the same as this sum right here. And we have already shown right at the beginning that this is necessarily unique. And we conclude our proof. Now, before we stop, one more corollary that we get from this, and it is very obvious. Corollary 1.13. We will not prove this explicitly. A sequence xn, as it is a basis on its closed linear hull, is a basic sequence if and only if all xn are non-zero and there exists a number m greater than 0 such that for all m1 and m2 with m1 less than m2, we get the following inequality that we have grown familiar with by now. So for all m2 greater or equal to m1. All right. Now, this is pretty obvious because every basic sequence is a basis on its closed linear hull, and thus these two criteria are the only ones left to fulfill the entire Grinblum criterion on the closed linear hull of the basic sequence, which makes it a basic sequence. So next up, in the next video, we will finish the topic of Schauder bases and then move on towards the second chapter, the isomorphic theory of spaces that are similar in a Schauder base sense to C0. Until then, bye bye.